Jupiter has protected Earth for billions of years, vacuuming up comets, nudging wandering rocks away, acting like a massive guardian in the dark. Except that's only half the story, because Jupiter doesn't only shield us. Sometimes it loads the gun. In March 2026, an interstellar visitor called 3I, Atlas 3 Atlas, will descend into Jupiter's gravitational well, and depending on the approach angle, it could leave on a trajectory that lines up with Earth, moving faster than anything we've ever tried to push off course. We have nuclear weapons. We have spacecraft. We have brilliant minds who can turn equations into engines. So, could we stop it? The physics says maybe. But the real answer is far more unsettling because saving Earth might be technically possible, yet humanly impossible. Stay with me, and you'll see why the hardest part may not be the rock, but us. If you're captivated by this unfolding scenario, consider subscribing so you can follow along as we track it in real time. And leave a comment telling us where you're watching from, what time it is in your corner of the world, and whether you think we're being told everything we need to know about what's truly at stake here. Part 1. The week the models broke. There's a date circled in red on calendars inside very quiet rooms at NASA, ESA, and a handful of other institutions most people never think about. March 2026. Not because something must happen that day, but because after that day, the math stops behaving the way it's supposed to. Scientists don't love talking about it in public because uncertainty sounds like doubt, and doubt sounds like incompetence, and incompetence gets your funding cut. But inside those rooms where coffee goes cold and screens glow past midnight, they're watching 3 Atlas with the kind of focus you reserve for things that could end the world. Orbital predictions usually improve with time. You spot an asteroid, track it for a few weeks, refine the numbers, tighten the fit, until you can tell someone where it'll be a century from now, with an error bar smaller than a city block. It's beautiful, almost soothing mathematics. Clockwork universe stuff. Newton would be proud. But 3 Atlas isn't playing by those rules anymore, and the reason has everything to do with where it's headed. Jupiter doesn't tighten predictions. Jupiter explodes them. Here's what happens when you try to predict the trajectory of something about to pass close to the largest planet in our solar system. You run your simulations. You input the object's current position, velocity, rough mass estimates, and you let the computer propagate forward through time. Standard procedure, except instead of getting a narrow cone of probable futures, you get something like a spray pattern across the black. Some versions of 3A Atlas slip past Jupiter and keep going into interstellar space, never to trouble anyone again. Some get captured briefly into chaotic, looping paths, and some, a small but non-zero percentage, come screaming back toward the inner solar system, with velocity vectors pointed in directions that make astrophysicists go very, very quiet. The technical phrase is chaotic sensitivity, which sounds academic until you feel what it means in your bones. A difference in initial position, smaller than the width of a human hair measured across millions of kilometers, can turn into an outcome difference measured in astronomical units. Miss 3 Atlas's velocity by a fraction of a percent today, and 6 months from now, that error could be the distance between safe passage and a collision course. It's not that the math is wrong, the math is perfect, reality is messy, and Jupiter's gravity is so stupendously powerful that it takes that messiness and amplifies it like a prism, splitting white light into 1,000 colors into a kaleidoscope of possible futures. What keeps scientists awake isn't the median outcome. Median outcomes are boring. Median outcomes say everything will be fine. What keeps them up is the tail end of the probability distribution, the outliers that show up in one simulation out of 10,000. Because when the consequence of that 1 in 10,000 outcome is the end of human civilization, extremely unlikely stops being comforting. You don't bet the species on favorable odds. You don't shrug at low probability extinction events. You lose sleep. Listen closely to how the language has shifted in technical papers published over the last year. 2 years ago, scientists said a collision with Earth was physically impossible given 3I, Atlas's trajectory. 1 year ago, that became extraordinarily improbable. 6 months ago, highly unlikely. Last month, unlikely. Do you see the pattern? Each refinement hasn't made the future cleaner. It's made it less certain. The window of possibility is widening, not narrowing, and that progression tells you everything you need to know about what Jupiter does to confidence. Jupiter isn't our shield. That's the comfortable story we've told ourselves for decades. Big Brother Jupiter sweeping up comets and asteroids, protecting fragile Earth from cosmic bombardment. It's a nice narrative. It's also incomplete, because Jupiter doesn't only deflect objects, it can accelerate them. It can take something moving at a manageable velocity and whip it back toward the inner solar system faster than anything natural has any right to move. The same mechanism that makes gravity assist so elegant for our spacecraft can turn chaotic encounters into catastrophes for everything else. What we're experiencing right now isn't a prediction of impact, it's a collapse of certainty. And in some ways, that's more dangerous because predictions, even bad ones, give you something to plan around. You can act, you can respond. But when the science fractures into 1,000 plausible futures, when experts hedge and publish papers with more caveats than conclusions, you lose the one thing you need most in a crisis: consensus, direction, the ability to move as one. Every week, new observations arrive. Every week, the uncertainty bands shift, sometimes narrowing, sometimes expanding. And every time they expand, somewhere in those quiet rooms, someone updates the probability calculations for the scenarios nobody wants to say out loud. The ones where 3 Atlas threads the needle through Jupiter's gravity well at precisely the wrong angle, picks up precisely the wrong amount of velocity, and exits onto a path that intersects Earth's orbit at precisely the wrong time. It's not a prediction, it's a possibility, and the possibility is growing. So here's the question nobody wants to answer aloud. What happens when the people we trust to understand the universe tell us they can't give us a clean answer anymore? What happens when scientists stop saying "don't worry" and start saying "we're not sure"? Because that is where we are. March 2026 is the event horizon, the point after which our ability to predict collapses in the wake of Jupiter. 3 Atlas could go anywhere, and we won't know which version of the future we're living in until it's far too late to change it. Part 2. How a gravity assist actually becomes a weapon. You've probably heard of gravity assists. NASA loves them. Every mission to the outer solar system uses them. Voyager, Cassini, Juno, New Horizons, gravitational billiards that steal speed without burning fuel. It's elegant, it's efficient, and when engineers do it, it behaves beautifully because the variables are controlled: approach angle, altitude, timing, mass, thrust corrections. They know where the spacecraft will be, and they know how Jupiter's gravity will bend the line. But when nature does it, when a chunk of ice and rock from another star system barrels through Jupiter's sphere of influence with no guidance, no control, just raw physics and chaos, that's when gravity assists stop being tools and start being weapons. The principle is simple enough you can picture it. Imagine a cue ball rolling across a table. Now imagine a much heavier ball cutting across its path at speed. If they meet just right, the cue ball doesn't merely deflect, it steals momentum and shoots off faster than before, in a new direction, as if the table itself had decided to change the rules. Jupiter is that heavy ball, except it isn't a little heavier. It's 318 times more massive than Earth. And it isn't rolling on felt, it's orbiting the Sun at about 13 kilometers per second, carrying momentum like a mountain in motion. Anything that passes close enough to Jupiter's gravity can exchange momentum with it, and because Jupiter has momentum to spare, what flies away can leave moving significantly faster than what flew in. Here's where it gets nasty. When NASA plans a gravity assist, they're aiming for a predictable outcome. They model down to the microsecond. But when an object approaches Jupiter on a chaotic trajectory with uncertain mass, uncertain composition, possibly tumbling, possibly outgassing, possibly asymmetric, you aren't planning a maneuver. You're rolling dice. The outcome depends on variables we can't measure precisely enough from Earth. Small differences in approach geometry can create enormous differences in exit velocity and direction. It becomes stochastic, probabilistic in all the ways that matter. Jupiter's mass is the ultimate amplifier. A tiny measurement error in 3i, Atlas's current state, can be multiplied during the encounter into a wildly different future. Think of it like trying to predict where a pinball will exit the machine by measuring where it entered. You can guess the general flow, but every bumper, every slight variation in angle, compounds. Jupiter's gravity field has bumpers everywhere. Its moons add perturbations. Jupiter itself isn't a perfect sphere. It's an oblate spheroid, rotating so the field is subtly moving, subtly asymmetric. All of these details conspire to turn small uncertainties into a huge spread of outcomes. There's a term in orbital mechanics called hyperbolic excess velocity, the speed an object has relative to a planet after escaping its gravitational influence. When you do a gravity assist right, you can increase this value substantially. Voyager 2, for example, approached Jupiter at about 5 kilometers per second relative to the planet and left with a heliocentric speed near 27 kilometers per second, a dramatic boost. Now imagine 3I, Atlas, already moving at interstellar speeds, threading Jupiter's well in such a way that it gains an additional velocity component pointed inward toward the inner solar system. The numbers stop being abstract and start feeling apocalyptic. People think gravity assists are precise because our spacecraft make them look precise. They aren't, by nature. They're controlled chaos. We make them precise only because we know everything about our spacecraft, its exact mass, position, velocity, and we plan the approach with obsessive detail. Even then, mid-course corrections are standard because reality never matches the model perfectly. But we don't have mid-course corrections for 3 Atlas. We don't have thrust. We don't have control. We have telescopic observations with error bars and simulations built on assumptions. And when you run those assumptions forward through a Jupiter encounter, the error bars don't shrink. They detonate outward. Timing becomes everything. If 3 Atlas reaches Jupiter's periapsis 3 hours earlier or later than predicted, it can exit onto a completely different trajectory. 3 hours. Over a month-long approach, that's almost nothing, a rounding error. But it can be the difference between a near miss and a direct hit. No intelligence required, no malicious intent. Just physics, probability, and catastrophically bad luck. The mythology around gravity assists treats them like precision instruments. They're not. They're opportunistic hacks of celestial mechanics. When you control the variables, they're miraculous. When you don't, they're roulette wheels. And we are absolutely, unequivocally not in control of what happens when 3 Atlas meets Jupiter. We're spectators. We're watching a cosmic game of chance where one of the possible outcomes is extinction. And we won't know which number came up until the wheel stops spinning, by which point, of course, it's too late to place a different bet. Part 3. The energy budget nobody likes to say out loud. Let's talk about energy, because at the end of the day, that's what kills you. Not the romance of the story, not the name of the rock energy. Specifically, kinetic energy, which scales with the square of velocity. Double the speed, quadruple the destruction, triple the speed, 9 times the devastation. And 3 Atlas, if it comes back from Jupiter moving anywhere near what the worst-case runs imply, it won't just be dangerous. It will be carrying more kinetic energy than anything to strike Earth since the dinosaurs had their last ordinary day 66 million years ago. For perspective, remember Chelyabinsk, February 2013, a roughly 20-meter asteroid burst over Russia with the force of about 30 Hiroshima bombs. Windows shattered across 6 cities. More than 1,000 people were injured. And it became the most documented meteor airburst in history because everyone in Russia has a dashboard camera. Chelyabinsk was terrifying, and it was a pebble. It released about 500 kilotons. Now scale up. Tunguska, 1,908, roughly 60 meters, an estimated 15 megatons, flattening 2,000 square kilometers of Siberian forest. No crater, because it exploded in the air, but the shock was felt across Europe like a distant door slamming shut. Still a firecracker compared to the big one, Chicxulub, the impact that ended the Cretaceous. Estimates place that asteroid at roughly 10 kilometers across, striking the Yucatan at around 20 kilometers per second. Energy released, somewhere in the neighborhood of 100 million megatons. 100 million. It vaporized the impactor, carved a crater about 200 kilometers wide, ignited global wildfires, and threw so much debris into the sky that photosynthesis stalled for years. 3/4 of all species went extinct. That is what kinetic energy at scale can do. Now here's the problem with 3 Atlas. We don't know exactly how big it is, and we don't know exactly what it's made of. Best estimates place it somewhere between 1 and 3 kilometers in diameter, but those are educated guesses built from brightness and assumptions about albedo. Could be bigger, could be denser than we think, could be lighter. Every variable feeds the energy calculation, and every variable has error bars wide enough to drive a truck through. But even using conservative numbers, if 3 Atlas picks up enough velocity from Jupiter to come back at, say, 50 kilometers per second, you're looking at an energy release that makes Tunguska feel like a hand grenade. Velocity dominates the equation. A 1-kilometer object at 20 kilometers per second is already measured in megatons. That same object at 50 kilometers per second, and you're no longer talking about a regional catastrophe. You're talking about a global one. The atmosphere won't save you at those speeds. It won't burn up. I have 240. It will punch through as if air were only a suggestion and deliver nearly every joule of kinetic energy straight into the crust. The shockwave alone could circle the planet. The ejector would darken the sky. And the environmental collapse afterward would make the aftermath of Chicxulub feel by comparison like a slow Tuesday. Now, let's talk about stopping it, because this is where the energy budget turns into a nightmare. Every deflection method we have relies on the same basic move: impart momentum, change the trajectory, change the future. Kinetic impactors ramming a spacecraft into an asteroid work beautifully for slow-moving near-Earth objects when you have years of warning. You don't need to destroy the object. You only need a tiny nudge, so that, over years, the nudge becomes a mist distance of thousands of kilometers. It's elegant. It scales perfectly for the kinds of threats we're used to. But 3 Atlas isn't a near-Earth object anymore. If it comes back from Jupiter, it's an Earth-crossing interstellar projectile, moving faster than anything we've ever tried to deflect. The momentum transfer required to nudge something that massive, moving that fast, is staggering. You could hit it with every kinetic impactor we could feasibly build and launch, and the velocity change would still be negligible. We're talking meters per second when you would need kilometers per second. Not even close. The physics don't scale, the energy budgets don't close, and fragmentation breaking it into smaller pieces doesn't solve it, because you're not removing energy from the system. You're only spreading it out. Instead of one extinction-level strike, you get a shotgun blast of smaller, but still catastrophic impacts scattered across the world. Congratulations, you've made the geometry worse. There's a brutal timeline calculus here that nobody wants to say plainly. Deflection works when you have time. Years of time. You can launch multiple missions, make small corrections, wait for the orbit to shift, confirm the new path. Repeat. But if 3 Atlas exits Jupiter on a collision course, the timeline from detection to impact could be measured in months, not years. And in that window, you don't have time for gentle nudges and iterative course corrections. You have time for one shot, maybe, and that one shot would need to work perfectly, with no margin for error, using technology we've never tested at these energy scales, against a target we don't fully understand, moving faster than anything we've ever tried to hit. So when people ask, can we stop it? The honest answer depends entirely on when you ask. Can we stop it if we knew 5 years in advance, with unlimited funding and true global cooperation? Maybe. Probably. Can we stop it if we find out 6 months before impact? The math says no. The energy budget says no. The timeline says no. And the worst part is, we won't know which scenario we're in until after Jupiter does its work, by which point the window for maybe may already be sealed shut. And then all we're left with is no, and the sound of very smart people trying to figure out how to say that without causing immediate global panic. Part 4. The nuclear option isn't a solution, it's a dice roll. When all else fails, there's always the nuclear option, literally. Actual nuclear weapons, the kind we built to vaporize cities, repurposed to vaporize asteroid surface material instead. It's humanity's ultimate trump card, a last, desperate gambit. When kinetic impactors won't cut it, and we're out of cleverness, detonate a multi-megaton warhead on or near the surface, superheat part of the body into plasma, and let ablation create thrust that pushes the object off course. In theory, it's brilliant. In practice, it's a coin flip with civilization leaning over the table. Here's how nuclear deflection is supposed to work. You don't try to blow up the asteroid that's Hollywood. You try to vaporize enough material on one side that the expanding gas becomes a temporary rocket engine. The object doesn't need to be destroyed. It only needs to be pushed. A few meters per second applied early enough can translate into thousands of kilometers of missed distance by the time it reaches Earth. The key phrase is early enough, because if you wait until the last minute, even a perfect detonation won't give you the trajectory change you need. Orbital mechanics is merciless about late interventions. And nuclear deflection has another problem. You have to know what you're hitting. Is the object solid rock? A porous rubble pile? Ice mixed with dust? Each responds differently to sudden heating. A dense metallic body might soak energy and barely budge. A loosely bound rubble pile might fragment instead of deflect, which, as we've established, is not an improvement. Comet-like objects, what 3 Atlas might be, are especially tricky. They're full of volatiles that can outgas unpredictably when heated. You might get more thrust than expected, or less. Or you might get a sideways shove that changes the spin and makes subsequent predictions even worse. Timing is everything, and timing is impossible. To intercept 3 Atlas after a Jupiter encounter, you'd need to launch before the encounter happens because you won't have time to design, build, and launch afterward. But launching before means you're guessing where 3I Atlas will be after Jupiter. So you're building an intercept trajectory on probability, not certainty. And if the object exits Jupiter on a different path than your median forecast, your multi-billion-dollar nuclear interceptor will sail through empty space while the real threat keeps coming. One shot. No do-overs. Then there's the political dimension, which makes the physics look straightforward by comparison. Nuclear weapons in space are constrained by the Outer Space Treaty of 1967, which bans weapons of mass destruction in orbit or on celestial bodies. You can argue a deflection mission isn't stationing a weapon, it's using one for planetary defense. But technicalities don't soothe geopolitics when you're asking nuclear powers to cooperate on launching live warheads beyond Earth orbit. Who builds it? Who controls it? Who decides when to detonate? What if it fails and the warhead falls back down? What if it works, but contaminates near-Earth space with fallout? These aren't imaginary worries. These are the kinds of questions that can trap UN committees for years. Now, fragmentation risk. This is the nightmare that keeps planetary defense experts awake. You hit the object with a nuclear blast. The surface ablates as expected, but the internal structure can't handle the stress, and the body breaks into multiple large fragments. Each fragment now follows a slightly different trajectory. Instead of one impact point, you've created several. Some might miss, some might hit. And now, rather than evacuating one city, you're trying to evacuate 3 continents, while hoping your fragment models are more accurate than your original models, which, remember, weren't solid in the first place. Fragmentation doesn't remove kinetic energy. It redistributes it. And redistributed badly is worse than concentrated. The uncertainty in 3 Atlas's internal structure is total. We've never examined an interstellar object up close. We have no ground truth. Is it a coherent body? Or a flying gravel pile held together by microgravity? We won't truly know until we hit it. And by then it's too late to choose a different plan. Every nuclear deflection model assumes something about structural integrity, and every assumption could be wrong. The difference between success and catastrophe might come down to an internal crack pattern we can't detect from Earth. Then there's yield. How big does the warhead need to be? Too small and you waste the mission. Too large and you increase fragmentation risk or trigger unpredictable outgassing. Optimal yield depends on mass, composition, structure, all of which are uncertain. So, you're designing a weapon from incomplete information, hoping your error bars are generous enough, knowing there isn't a second chance. At that point, it's not engineering, it's educated gambling. And even if everything goes perfectly, if you nail the intercept, place the device correctly, choose the right yield, and the object deflects cleanly without fragmenting, you still inherit the propaganda problem. Half the world calls it a triumph of science and cooperation. The other half says it was unnecessary, that the threat was exaggerated, that it was an excuse to normalize weapons in space under the banner of planetary defense. Conspiracy theories spread faster than corrections, and the next time scientists warn about an impact, a non-trivial slice of the public won't believe them because distrust has been trained into the system. The nuclear option isn't a solution. It's a last-ditch, low-probability Hail Mary we attempt because the alternative is doing nothing. And maybe it works. Maybe we get lucky. Maybe the physics align, the politics cooperate, the engineering holds, and 3 Atlas is nudged just enough to miss. But betting the survival of the species on maybe is not a plan. It's a prayer. And prayers have a mixed track record when it comes to stopping rocks from falling out of the sky. It's set by bureaucracy. By the time you know for certain that 3 Atlas is coming, it's already Part 5. The real deadline isn't Impact Day. Here's the thing people rarely understand about existential threats. The deadline is almost never the moment the asteroid arrives. The real deadline comes earlier, quietly, and it usually isn't set by physics at all. It's set by paperwork, permissions, and the slow grind of human systems. By the time you know with certainty that 3 Atlas is coming, it's already too late to stop it, because stopping it would have required decisions made months, sometimes years before certainty ever existed. Extinction doesn't happen in one dramatic second of impact. It forms in 1,000 tiny failures to act, each delay defensible on its own, all of them, together, fatal. So let's walk through what a real planetary defense timeline looks like. First, detection and confirmation. Multiple observatories have to agree the object is real and the track is real. That takes weeks, sometimes months, because you need enough data points to separate a true trajectory from measurement noise and natural drift. Then comes analysis and modeling. Teams around the world run simulations, compare outputs, argue about assumptions. More weeks. Then you need consensus. Not just, there's a risk, but how big the risk is and what the probability truly means. If one major group sees a 5% impact chance and another sees 15%, you don't get unity. You get meetings. And once you have consensus, you still need political authorization. This is where everything tends to die in the hallway. Politicians don't greenlight multi-billion-dollar crash programs based on probabilities they don't intuitively understand. They authorize based on certainty. And certainty is the one thing you don't get until it's too late to matter. So you get more panels, more risk assessments, more budget reviews, more international consultations. Everyone wants one more tranche of data before committing. And every week spent waiting for better confidence is a week not spent building the thing that would actually have to fly. Suppose somehow you get authorization anyway. Now you need design and construction, even using familiar technology. A nuclear interceptor isn't a modified missile, it's a deep space spacecraft. It has to travel millions of kilometers, intercept a small, fast-moving target with needle thread accuracy, and deliver a payload under conditions we've never tested at this scale. Every component must be designed, built, tested, integrated, and tested again. Shortcuts don't mean speed. Shortcuts mean failure. And failure means the mission fails because there are no do-overs. Then come launch windows, another constraint people forget until it's too late. You can't launch whenever you feel emotionally ready. You need geometry. You need the target in the right place relative to Earth, and the spacecraft in the right energy corridor to reach it. Miss a window and the next one may be weeks away, and in those weeks the intercept geometry can drift out of reach. Worse, if 3 Atlas's post-Jupiter path is still uncertain, you're not aiming at a point. You're aiming at a probability cloud, and even a perfect launch can end in empty space. Here's the killer. Jupiter creates a cutoff date that has nothing to do with impact day, and everything to do with reachability. If we're going to intercept 3I, Atlas, we likely have to do it before it gets too close to Earth, because once it's close enough for ground systems to track precisely, it's moving too fast for a fresh intercept mission to catch. The practical deadline is probably sometime before or shortly after the Jupiter encounter, which means we'd have to decide to build and launch while we're still uncertain whether we even need to. We'd be betting billions of dollars and years of effort on an evolving probability distribution. But uncertainty breeds paralysis. Every model has error bars. Every prediction has confidence intervals. And as long as there's a chance that more observations will narrow the uncertainty, there's an incentive to wait. Politicians don't want to fund a threat that might evaporate. Scientists don't want to cry wolf and burn credibility. And while everyone waits for certainty, the launch window closes, the geometry becomes impossible, and the decision is made by default. We choose an action by failing to choose an action. This is the paradox of probabilistic threats. Act early, and you risk spending vast resources on something that never happens. Wait for certainty, and you discover you waited too long. There is no comfortable middle ground. You either accept the risk of a false alarm or accept the risk of being late. And historically, institutions lean toward inaction because a failed prediction is career-ending, while delayed action can always be blamed on insufficient information. In this scenario, extinction wouldn't be decided on impact day. It would be decided months earlier, in conference rooms and budget hearings. When someone asks for more data and everyone agrees it sounds reasonable, it would be decided when schedules slip because a component fails testing and nobody wants to bypass protocol. It would be decided when international coordination fractures because one nation wants veto power over deployment. Death by 1,000 reasonable-sounding delays. Each one defensible. All of them, together, suicidal. The real deadline is the last moment we could have started building the thing that might save us. And we won't know when we passed it until long after it's gone. That's the horror. Somewhere between now and impact, there's an invisible point of no return, and we will glide right past it while arguing about data quality and funding priorities. Convinced we still have time, because impact is still months away. But impact is the last thing that happens. The failure happens first, quietly, in the space between decision and action, while we wait for a certainty that may never arrive in time. Part 6. Why the data will never fully agree. Want to know why the predictions keep shifting? Why every new observation seems to complicate instead of clarify? because 3 Atlas isn't a clean billiard ball. It's a tumbling fragment of ice and rock, changing as it moves. And those changes push its path in ways that are fundamentally hard to model from millions of kilometers away. The technical phrase is non-gravitational forces, boring words for something profoundly inconvenient. As a comet-like object warms near the sun, volatiles sublimate. Jets of gas and dust vent outward, often asymmetrically, because the surface is patchy and scarred. Each jet is a tiny rocket engine, a whisper of thrust, applied continuously, that nudges the object off the pure gravity prediction. And from Earth, we don't see the jets clearly. We see a faint smear, maybe a coma if we're lucky. But which regions are venting? How strongly? And in what direction? That becomes inference layered on assumption. And rotation makes it worse. If 3 Atlas is tumbling, and it probably is, those jets sweep through space like a broken sprinkler. The net force depends on rotation rate, orientation, volatile distribution, and a dozen other properties we can't measure directly. So you model statistically using what solar system comets tend to do, but interstellar visitors may not behave like anything we've catalogued. Assumptions carry error bars, and error bars propagate. Then there's asymmetric mass loss. As the object sheds material, it doesn't shed evenly. One hemisphere might be richer in ice, another dustier, tougher, darker. The mass distribution shifts over time, which changes how the object responds to sunlight, outgassing, and subtle pressures, which changes the trajectory again, like a feedback loop in slow motion. Every attempt to pin down its future has to account for these effects. And accounting for them means choosing a model. Different teams choose different priors, different weightings, different interpretations. That's why you get different answers from honest people reading the same sky. Look at the published confidence intervals for 3 Atlas after Jupiter. They're enormous. Some groups predict a passage near Earth's orbit, with a missed distance of millions of kilometers. Others can't fully rule out trajectories that intersect Earth's orbit itself. The differences aren't necessarily wrong versus right. They're what you get when the same sparse data supports a wide range of plausible physics. And without better observations or closer approaches, we can't discriminate cleanly. This isn't scientific incompetence. This is reality being legitimately uncertain. The plots shown in press releases are tidy, clean curves, neat shading. But behind those plots are Monte Carlo runs. Thousands of iterations, tiny shifts in initial conditions. The outputs form clouds, not lines. Some of those clouds cross Earth's orbit. Some don't. Which cloud you emphasize depends on how conservative you decide to be. And that becomes a value judgment wearing the mask of statistics. Different observatories use different instruments with different calibrations. Optical telescopes see one slice of truth. Radar, when available, sees another. Space-based platforms have their own biases compared to ground-based surveys. Every dataset must be cross-calibrated, adjusted for systematics, weighted by confidence, and there's no single perfect recipe for combining heterogeneous sources. So you get papers citing the same nights of observation, yet reaching different conclusions because they processed the data differently. Disagreement breeds mistrust. The public hears experts diverge and assumes nobody knows anything. Politicians see overlapping confidence intervals and decide the threat is not real enough to fund. And meanwhile, scientists are trying to explain the hardest truth. Uncertainty isn't ignorance. It's honesty about the limits of measurement in a chaotic system. Here's the brutal truth. The data will never fully agree. Not before Jupiter, and not after. Because each new observation tightens some uncertainties, while revealing new complications. Every model improvement uncovers a detail we didn't know we needed. The closer we look, the more we realize how much we can't directly see. And that is terrifying to a world that wants a binary answer. Is it going to hit us or not? When will you know? How sure are you? And the only completely certain answer is, we'll know when it either hits or misses. Even then, we'll debate whether our predictions were truly validated or simply lucky. This irreducible fuzziness becomes the perfect excuse for inaction. Because if scientists can't present one unified number, how can politicians justify committing? If the error bars are wide, why not wait for better data? And every week spent waiting is a week closer to the moment when better data won't matter, because there won't be time left to act on it. And even then, we'll still be arguing about whether our forecasts were truly validated or whether we simply got lucky this time. That uncertainty, that irreducible haze in the data, becomes the most convenient excuse for doing nothing. Because if the scientists can't agree, how can we expect politicians to commit? And if the confidence intervals are that wide, the temptation is always the same. Wait for better data. And every week spent waiting is 1 week closer to the moment when better data won't matter, because we've run out of time to act on it. Uncertainty is paralyzing. It's the gap, the quiet, yawning space where collective action goes to die. Part 7. The silent assumption behind planetary defense. Every planetary defense plan you've ever read carries one hidden assumption so basic that nobody bothers to say it out loud. The assumption is this: when the chips are down, humanity will cooperate. Faced with extinction, nations will set aside their differences, pool their resources, and work together to save the species. It's a beautiful idea. It's also almost completely unsupported by history. Planetary defense, as it's imagined today, demands a level of global coordination we've never truly achieved, except, maybe, in rare cases like eradicating smallpox. And that took decades, and it happened because the threat was visible, immediate, and killing people right now. An asteroid months from impact is abstract. It's probabilistic. It's a computer model, not a body count. And asking nuclear powers to cooperate on building and deploying nuclear weapons in space based on probability distributions means you're not talking about science anymore. You're talking about geopolitics, sovereignty, and the accumulated mistrust of centuries. There is no central authority for existential threats. The United Nations has committees. It has working groups. It has cooperation frameworks that function beautifully when the stakes are low and everyone's interests align. But when you're asking countries to spend billions on a joint mission that might fail, or worse, might succeed but benefit some nations more than others, those frameworks start to crack. Who decides where the mission launches from? Who controls the weapon? If the object fragments and some pieces hit while others miss, who's liable? If a nuclear deflection attempt fails and the warhead falls back to Earth, who is responsible? The legal framework is a patchwork of treaties written decades ago by people who never imagined we'd be in this. Our situation. The Outer Space Treaty bans weapons of mass destruction in space, but allows scientific research. So is a nuclear interceptor a weapon or a scientific instrument? Depends who you ask. The Liability Convention says launching states are liable for damage caused by their space objects. Does that apply to a deflection mission that fragments the asteroid? Probably. And does that mean no one will volunteer to launch it? Also, probably. Launch infrastructure is concentrated in a handful of countries. The United States, Russia, China, and maybe the European Space Agency, if they can agree among themselves. Everyone else becomes a spectator. But spectators don't stay quiet when their survival is on the line. If the launch states decide to act, do they need consent from the rest of the world? If they don't get it, do they act anyway? And what happens when some countries view the deflection attempt as a greater threat than the asteroid itself, because they believe the technology will be weaponized later? Veto power becomes a suicide pact. Historical precedent isn't encouraging. Look at climate change. The threat is global. The science is clear. The consequences are catastrophic. And yet, decades after the problem was identified, coordination is still fractured, commitments still weak, and emissions still rising, because every nation waits for others to move first. Now compress that timeline from decades to months. Raise the stakes from gradual warming to immediate extinction, and add nuclear weapons to the mix. Does that sound like a recipe for cooperation? Consider the incentives. If you're a small country with no space program, the rational strategy is to free ride. Let the big powers spend on planetary defense while you conserve resources for recovery afterward. If you're a major power with launch capability, your optimal strategy is to control the mission, so you can't be blamed if it fails. If you're a rival power, your optimal strategy is to cast doubt, to prevent your adversary from gaining prestige or technological advantage. Everyone acts rationally inside their own interests, and the collective result is paralysis. Then there's the question of consensus. What impact probability justifies action? Beifenjawu, Beifenjashe, Beifenjawusha. Different countries will have different thresholds. Some will want to act on any non-zero probability. Others will demand near certainty before committing resources. And there's no objective way to settle that dispute, because at its core, it's a values question, not a scientific one. How much are you willing to bet on being wrong? How much are you willing to risk by doing nothing? Those are political questions, and politics is not a consensus engine. Planetary defense plans assume we'll bypass all of this in a crisis. They assume rational actors making optimal choices under time pressure, But people don't become more rational under pressure. They become more tribal, more suspicious, more focused on the short-term survival of their in-group at the expense of the collective. Every crisis in history has shown the pattern. When resources feel scarce and the stakes feel existential, cooperation collapses. We don't always band together, we fracture. So when you read about a coordinated global response to deflect an asteroid, ask yourself, who's coordinating? Who has the authority to bind sovereign nations? Who resolves disputes when time is running out? The answer is nobody. There is no mechanism. Planetary defense is an idea without an institution, a plan without a planner, a defense without a defender. It's a fantasy of cooperation projected onto a species that has never, in its entire history, cooperated at the scale and speed something like this would require. Part 8. The Lifeboat Incentive. There's a certain kind of logic that appears the moment you admit cooperation might fail. If the collective can't save itself, maybe a subset can. Not everyone, but someone, enough to preserve continuity, enough to rebuild. It's called lifeboat logic. And once it takes hold, it redirects resources away from solving the problem and toward ensuring that certain people survive despite the problem. It's rational, it's cold-blooded, and it might already be happening. Imagine the world 6 months after Jupiter, when the probabilities start firming up, and they aren't favorable. Governments are gridlocked. International cooperation is stalling. The engineering timeline for a deflection mission is slipping, and into that widening gap steps an idea. What if we can't save Earth, but we can save some humans? What if, instead of betting everything on a Hail Mary deflection, we start building backups? Mars colonies suddenly look very attractive. Not because Mars is pleasant. It's not. It's a frozen, radiation-blasted desert where you live inside a glorified tin can, eating hydroponic vegetables. But it's not Earth, which means if something hits Earth, Mars survives. Orbital habitats, same logic. Lunar bases, same logic. Anywhere outside the blast radius becomes a potential refuge. And if you have the money and connections to buy a seat on that refuge, why wouldn't you? History is full of elite exit strategies. When Rome fell, the wealthy retreated to fortified villas. When the Black Death hit, the rich fled to the countryside. During wars, those with resources evacuate, while those without stay and die. It isn't always malice. It's self-preservation, filtered through access to capital. If you can escape a threat others can't, and escaping raises your survival odds, leaving becomes the rational choice. Capital flows towards survival. If the smart money decides Earth is doomed, it flows toward anything that isn't Earth. Space companies that struggle to raise funding suddenly have more investors than they can handle. Mars colonization projects that stalled for lack of interest become fully subscribed overnight. Orbital habitat designs shelved as economically unviable get greenlit with blank checks. And every dollar that pours into lifeboats is a dollar not spent on planetary defense. The messaging shifts too. It isn't framed as abandonment, it's framed as backup humanity, preserving the species, ensuring continuity of civilization. And technically, yes, that's true. A Mars colony would preserve human DNA, culture, and knowledge. But when the resources required to build that colony could have gone toward deflecting the asteroid, potentially saving 8 billion people, instead of 800, the calculus starts to look less like species preservation and more like expensive triage. The rich decide they're worth saving, and everyone else becomes acceptable loss. There's a feedback loop here. As lifeboat projects gain funding, planetary defense is starved. As planetary defense is starved, its probability of success drops. As that probability drops, lifeboats look even more attractive. And if you're wealthy enough to have options, the rational move is to secure your seat early, before the price climbs, and the act of doing so makes the collective solution less likely, which makes lifeboats more necessary, which accelerates capital flight away from Earth. Corporate interests align with lifeboat logic too. Space companies make more money building colonies than deflecting asteroids. There's no profit model for planetary defense. It's a one-time project with massive risk and no ongoing revenue. But a Mars colony, that's subscriptions, supply chains, real estate, infrastructure, it's a business model, and business is optimized for revenue, not altruism. If the market says build lifeboats, lifeboats get built. National governments might pursue the same logic. A country with a viable space program might quietly decide that saving some of its citizens is more achievable than saving all of Earth. Launch a small, elite group to a prepared orbital station or a lunar base. Preserve the nation's genetic and cultural legacy. Frame it as a contingency plan, not an evacuation. And if other countries find out, so what? They'll do the same if they can. It's game theory. The first mover gets the best odds. Everyone else scrambles for what's left. This isn't necessarily evil. It's incentive-driven. People respond to incentives. And when the incentive is survival versus extinction, morality becomes a luxury. The question isn't whether lifeboat logic is good or bad. The question is whether it's already happening. Are there quiet conversations in boardrooms and cabinet meetings about continuity of leadership? Are contingency plans being drafted that assume Earth impact and plan for post-impact recovery from off-world assets? We wouldn't know. And if we did know, would it change anything? Because even if you're morally opposed to abandoning Earth, if someone offers you a seat on the lifeboat and the alternative is certain death, you take the seat. The final dark twist is that lifeboat logic might be correct. If planetary defense truly has a low probability of success due to coordination failure, then preserving some humans off-world is better than preserving none. Better that civilization continues somewhere than nowhere. And if that's true, then the most rational move for anyone with resources is to secure their own survival and the survival of as many others as they can afford, and accept the rest as tragedy, unavoidable. Cold math. 800 survivors beats 0 survivors. And if the alternative is betting everything on a failing collective effort, maybe lifeboats aren't betrayal. Maybe they're wisdom. Part 9. Controlled disclosure versus public panic. Let's talk about what you tell people when the math starts looking bad. Do you tell the truth, all of it immediately? Or do you release it slowly, managing the message, controlling the narrative, so that when people panic, they panic in ways you can still steer? Because make no mistake, there will be panic. The question is whether it becomes productive panic that drives action, or chaotic panic that accelerates collapse. Governments delay worst-case disclosures. It's standard practice, not always because they're evil, but because information is destabilizing. If you announce there's a 10% chance of an extinction-level impact in 6 months, what happens? Markets crash. Supply chains seize as people hoard. Infrastructure workers abandon their posts. Societal trust evaporates. You trigger the collapse you're trying to prevent, even if the impact never happens. So you hedge. You emphasize uncertainty. You talk about ongoing analysis. You reassure the public that experts are monitoring the situation, and you hope that by the time the truth becomes unavoidable, you've bought enough time to build a plan. Market sensitivity to existential risk is extreme. Financial systems are built on the assumption of continuity. Stock valuations depend on future earnings. Bonds depend on repayment. Currency depends on governments surviving long enough to back it. Introduce genuine uncertainty about whether civilization continues, and those assumptions begin to dissolve. Why pay your mortgage if the world might end? Why invest in a company that might not exist? Rational actors liquidate, hoard essentials, and prepare for collapse. And when everyone does that at the same time, it becomes a self-fulfilling prophecy. Information asymmetry is the gap between what institutions know and what the public knows. In a crisis, that gap widens. Scientists know the models are drifting toward worse outcomes. Government officials know coordination is failing. Corporate boards know capital is being allocated towards survival rather than solutions. But the public hears reassurances, phrases like low probability, continued monitoring, no immediate threat. That gap between institutional knowledge and public messaging is where conspiracy theories breed. Past crises offer mixed lessons. The 2008 financial collapse was preceded by months of insider awareness while public assurances continued. And when the fall came, trust cratered. Early COVID messaging involved delays, mixed signals, and reassurances that later proved optimistic, and trust cratered again. People learn that official statements can be managed narratives, not transparent truth. And once that lesson sets in, it's almost impossible to unlearn. Future warnings get filtered through cynicism. Transparency has costs. If you tell people the unfiltered truth about probabilities, uncertainty, and expert disagreement, you can undermine confidence in your ability to handle the crisis. If you admit you don't know whether deflection will work, people hear incompetence. If you admit coordination is failing, people hear inevitability. Honesty becomes self-defeating because the public doesn't crave nuance. They crave certainty. And leaders who can't provide certainty get replaced by leaders who promise it, even if the promise is a lie. Social media amplifies everything. Rumors spread faster than corrections. Panic is contagious. Misinformation can look identical to information unless you're an expert, and most people aren't. A single viral thread claiming the government is covering up the real impact probability can reach millions before fact-checkers even notice it exists. And once a narrative takes hold, debunking it becomes nearly impossible, because corrections never travel as far as the original claim. Partial truth can be worse than full truth or no truth. If you admit there's a threat but downplay it, and later the severity increases, you burn credibility. People assume you lied the first time, so they won't believe you the second. But if you emphasize worst-case scenarios up front, you can trigger panic even if the worst case never materializes, which also burns credibility. There's no clean path. Every disclosure strategy carries a cost. Who controls the narrative matters. If scientists control it, they emphasize uncertainty and probabilities, which many people find unsatisfying. If governments control it, they emphasize reassurance and preparation, which scientists may find misleading. If media controls it, they emphasize drama and conflict, which both scientists and governments may find irresponsible. No single institution holds enough authority or enough trust to manage the message cleanly. So the story fractures into competing narratives, each side accusing the others of exaggeration or concealment. The ethical dilemma is unsolvable. Do you have a duty to tell people the truth, even if it causes harm, or a duty to manage information to minimize harm, even if it requires deception? Different ethical frameworks give different answers. Utilitarians might argue for controlled disclosure to maximize overall welfare. Deontologists would argue for transparency, no matter the consequences. And while ethicists debate in warm lecture halls, people out in the real world are making choices on incomplete information, choices with life and death weight. Meanwhile, the clock keeps turning. Every day you delay disclosure is a day people can't prepare. But every day you delay is also a day the situation might improve, more data might arrive, or coordination might finally click into place, making panic unnecessary. The perfect moment to speak is unknowable in advance. You only learn later, in hindsight, whether you spoke too early or too late. And in this scenario, there's no second attempt, no redo, no gentle correction. Part 10. The Dark Mirror Hypothesis. Here's a thought that should keep you awake at night. What if the asteroid never hits, and we still go extinct? What if simply knowing it might hit is enough to collapse us? That's the Dark Mirror Hypothesis. A credible existential threat can make civilization unravel, even if the threat never materializes, because the anticipation of doom becomes psychologically and economically indistinguishable from doom itself. The shadow can do the damage, even if the object never arrives. Economic systems are built on credit. Credit is built on trust, and trust is built on the assumption that tomorrow still exists. If the future becomes genuinely uncertain, credit stops flowing. Banks stop lending because borrowers might not exist to repay. Businesses stop investing because returns might never come due. Supply chains freeze because contracts become unenforceable. You don't need the asteroid to hit to break the economy. You only need enough people to believe it could hit, and once the economy goes, everything else follows. Supply chains are fragile by design: just-in-time logistics, minimal redundancy, and the assumption that transportation networks keep humming in the background. Introduce real uncertainty about whether those assumptions hold, and the whole system seizes. Truck drivers abandon routes because fuel might not be available at the next stop. Port workers stop unloading ships because the cargo might not have buyers. Warehouses stop restocking because manufacturers have halted production. Within weeks, grocery shelves empty. Within months, hunger spreads. Not because the asteroid struck, but because people believed it might. Timeline uncertainty is psychological poison. If you knew the asteroid would hit in exactly 6 months, you could plan, spend time with loved ones, settle affairs, make peace. But if the probability shifts every week with new data, you're trapped in limbo, too uncertain to give up, too afraid to hope. That sustained ambiguity erodes mental health, raises suicide rates, and destabilizes communities. People stop going to work not because the world has ended, but because they can't bear not knowing whether it's ending. Social trust is the glue of civilization, and under existential threat, that glue dries and cracks. Why follow laws if enforcement might collapse? Why pay debts if creditors might not survive? Why cooperate with strangers if you might need those resources for yourself? Every interaction becomes a prisoner's dilemma. Cooperate and risk exploitation, or defect and guarantee short-term survival at the cost of collective welfare. Rational actors defect. Society fractures. Panic doesn't require certainty. It requires perceived inevitability. Once enough people believe collapse is coming, they behave in ways that cause collapse. Bank runs happen because people think banks will fail, which makes banks fail. Riots happen because people expect order to break, which breaks order. Hoarding happens because people fear shortages, which creates shortages. Collective behavior driven by fear becomes self-fulfilling, and there's no simple mechanism to stop it, because telling people not to panic often makes them panic harder. Historical analogues are imperfect, but they're suggestive. The Black Death killed perhaps a third of Europe, and the social and economic upheaval lasted generations. The collapse of the Roman Empire wasn't one clean event, it was a cascade of failures, as institutions lost legitimacy and people stopped cooperating. The Great Depression showed how psychology can amplify economic collapse far beyond the initial shock, and those were crises that actually happened. Now imagine the psychological impact of a crisis that might happen, sustained for months, with no resolution. The dark mirror hypothesis says extinction doesn't require impact. It requires the belief that impact is probable enough. And once that belief spreads, civilization's mechanisms begin to fail because they're built on assumptions about the future that no longer feel true. You don't need to kill 8 billion people with a rock. You just need to convince them the rock is coming, and they'll do the rest to themselves. That creates a horrifying catch-22. If you don't disclose the threat, you can't mobilize resources to stop it. If you do disclose the threat, you might trigger collapse before the threat ever materializes. One optimal strategy might be to disclose only to elites who can work on solutions, while keeping the broader public in the dark. But that's exactly the kind of information asymmetry that breeds mistrust and conspiracy theories. And when the truth eventually leaks, collapse accelerates. There's no clean option. Every path leads to some version of catastrophe. So the question becomes, is survival psychological or physical? If people truly believe civilization is ending, does it matter whether the asteroid actually hits? Because by the time we find out, the civilization that might have stopped it may no longer exist. Extinction by anticipation, death by prophecy. And the cruel irony is that if the asteroid misses, we may never know whether we could have survived it, because we might have already destroyed ourselves preparing for it. Part 11. AI discovered physics we don't understand yet. Something strange is happening in physics labs around the world, and it has everything to do with machines finding patterns humans can't see. In the last few years, artificial intelligence systems have started finding solutions to orbital mechanics problems that work provably, yet no human physicist can truly explain them. The math checks out, the simulations confirm it, but ask why it works, and the researchers shrug. The AI found it. We don't know why it's right. We only know that it is. That matters for 3 Atlas, because some AI-discovered solutions involve trajectories near Jupiter, paths classical models labeled unstable, but which turn out to be metastable under conditions we didn't think to test. The AI doesn't think like we do. It doesn't care about intuition or familiar physical storytelling. It explores parameter space exhaustively, trying combinations no human would bother with because they look nonsensical. And sometimes those nonsensical combinations work. And if AI can find stable behavior where we thought none existed, what else is it finding that we aren't even asking about? The problem with black box predictions is trust. If an AI tells you 3 Atlas has a 15% chance of collision and shows you a trajectory that seems impossible, do you believe it? The model has been right before. Its track record is better than human-generated predictions. But you can't audit the reasoning. You can't trace the logic step by step and verify each assumption. You're trusting an alien intelligence, one that operates on principles you don't understand. And when the stakes are extinction, blind trust feels like abdication. Comprehension versus accuracy becomes the new divide. Humans want to know why something is true, not just that it's true. We want explanations, mechanisms, causal chains, but AI doesn't provide those. It provides answers. And if the answer is accurate but incomprehensible, do we act on it? Ignore it? Spend months trying to reverse engineer the AI's reasoning while the clock ticks down? The AI doesn't care whether you understand. It's simply showing what the math suggests. And that connects directly to predicting threats we can't explain. If AI models start producing impact probabilities that disagree with human models, and we can't figure out why the AI is saying what it's saying, we're in a nightmare scenario. Trust the AI and risk acting on a false alarm. Ignore the AI and risk missing a real threat. Split the difference and you're back to gridlock. Except now, You've added an inscrutable machine learning model to the list of things people argue about in committee meetings. Compare this to earlier scientific revolutions. When quantum mechanics emerged, physicists couldn't explain it intuitively, but they could derive it from first principles and show the math. When relativity challenged common sense, Einstein could walk you through thought experiments. But AI discovered physics doesn't arrive with a proof. It arrives with a confidence score and a training dataset. The epistemology is different. We've never had to decide whether to trust predictions we can't verify, generated by processes we don't understand, with stakes this high. So the question becomes, is explanation required for action? If an AI says deflect the asteroid and provides a method, do we need to understand why the method works before we try it? Normally, yes, because untested methods can fail catastrophically. But if the AI has simulated the method 10,000 times and shows it works in 95% of cases, is that enough? How much understanding do you need before you bet civilization on it? And that ties back to 3 Atlas uncertainty in uncomfortable ways. If our best models are AI-generated and we don't fully understand them, then the uncertainty isn't just about the object's trajectory, it's about our tools. We're using instruments we can't fully comprehend to predict outcomes we can't verify, and then making life or death decisions based on those predictions. It's epistemological vertigo. The ground beneath science itself begins to feel unstable. There's a deeper fear here. If AI starts making predictions that consistently outperform human experts, but the predictions remain inexplicable, what happens to science? Does it become a black box where we input observations and output policy without understanding the middle? Do we become cargo cultists of our own technology, trusting the oracle because it has been right before, but unable to check its work? And if future warnings come from AI systems, and those warnings contradict human intuition, how do we decide what to believe? The worst-case scenario is that AI discovers an outcome humans haven't considered, a trajectory, a mechanism, a failure mode, and it tries to communicate the warning, but we don't understand it. So we dismiss it as a model artifact or overfitting. And then the thing the AI tried to warn us about happens. And in hindsight, we realize the signs were there, but we couldn't read them because the language of the warning was too alien. Cassandra as algorithm, prophecy as training loss. AI becomes an oracle, not a tool. Oracles don't explain. They pronounce, and historically, people who ignore oracles suffer for it. But people who follow oracles blindly suffer too. We're entering an era where our ability to predict may outpace our ability to understand. And that gap is where catastrophe lives. Because you can't fix what you don't understand, and you can't trust what you can't verify. And yet the predictions might be accurate anyway. Welcome to the future. It's illegible. Part 12. Fusion breakthroughs that arrive too late. December 2025. Scientists at the National Ignition Facility achieve sustained fusion gain for the 5th consecutive month net positive energy. The dream of limitless clean power, decades in the making, finally realized. The announcement dominates headlines for a day, then everyone goes back to watching the sky. Because what good is unlimited energy if you don't have unlimited time? Fusion was supposed to save us, not just from climate change or scarcity, but from scenarios exactly like this one. Imagine if we'd had practical fusion power 30 years ago. The space program would look completely different. Fusion-powered spacecraft could accelerate continuously, reaching the outer solar system in weeks instead of years. Intercept missions would be routine. We'd have infrastructure quietly waiting, so a threat like 3 Atlas would be an astronomical curiosity, not a desperate wager. Deflection would be logistics, not a Hail Mary. But we didn't get fusion 30 years ago. We got it now. Too late to build the infrastructure. Too late to design and test fusion-powered interceptors. Too late to do anything except look at what we could have had and realize the solution existed in theory the entire time. We just couldn't build it fast enough. The universe doesn't care about your development timeline. This is a pattern, decades-long delays between identifying a solution and implementing it. We understood the physics of fusion in the 1,950 seconds. But going from theoretical possibility to practical reality took 70 years of incremental progress, funding battles, technical setbacks, and false starts. And now that we have it, the crisis it could have solved is already in motion. The timing is almost cosmically cruel. Compare it to climate change. We've understood the greenhouse effect since the 1800s. We've had viable renewables for decades, but deployment moved too slowly, constrained by politics, economics, and inertia. And now we manage consequences instead of preventing them. The pattern repeats. Problem identified, solution discovered, implementation delayed, crisis arrives in the gap. Humanity running 10 years behind on every challenge that matters. Planetary defense funding cycles follow the same logic. When there's no immediate threat, funding dries up. Why spend billions on hypotheticals? Then a threat appears, and suddenly everyone wants solutions yesterday. But you can't build critical infrastructure on short notice. You can't compress decades into months because you finally decided it matters. The gap between recognition and readiness is where extinction events slip through. There's a tragic pattern here. Solving problems after the crisis arrives. We become experts at aftermath. Vaccines arrive after pandemics. Regulations come after crashes. Safety standards follow disasters. We're excellent at learning from mistakes and terrible at preventing them. And for certain mistakes, extinction-level impacts, you don't get to learn. You just get to be extinct. If fusion had arrived on schedule, we'd have fusion-powered tugs parked in stable orbits, ready to intercept threats with weeks of notice. We'd have deep space monitoring networks powered by compact reactors. We'd have the energy budget to run continuous, high-precision tracking of every wandering object in the solar system. The infrastructure would exist, and 3I, Atlas, would be a fascinating visitor, not a potential catastrophe. But the infrastructure doesn't exist, and you can't build it now. The timeline doesn't allow it. The cruel irony is that fusion progress will likely accelerate from here. Next year, better designs. 5 years from now, compact fusion reactors. 10 years from now, fusion drives for spacecraft. All the capabilities we needed for 3 Atlas, arriving just in time to handle whatever comes next, assuming there is a next. Technological optimism becomes a trap when it delays action. If you believe the breakthrough is coming, you can justify waiting instead of using existing, less elegant technology. Why build a nuclear interceptor with chemical rockets if fusion drives are 10 years away? But what if the threat arrives in 5? Then you've spent 5 years waiting for better tools, and now you don't have time to use any tools. Optimism about tomorrow becomes an excuse for inaction today. The question is whether civilization learns fast enough, not whether we can solve problems, but whether we can solve them before the problems solve us. And the evidence so far suggests we're chronically too slow. We muddle through crises we could have prevented. We develop solutions after we needed them. And we tell ourselves it will be different next time, that we'll be ready, that the lesson has been learned. But the lesson never sticks, because the people making decisions now weren't the ones who suffered last time we were too slow. Jupiter's deadline doesn't care about fusion breakthroughs. It doesn't care that we're on the cusp of having the tools we need. Physics is indifferent to human progress. And if 3 Atlas comes back wrong, history won't remember that we almost had fusion. It will only record that we didn't have it when it mattered. Close counts in horseshoes. In asteroid deflection, close is the difference between a future and a fossil record. Part 13. The quiet rise of autonomous weapons in space. While everyone's been watching the asteroid, something else has been happening overhead. Satellites with decision-making capability. Autonomous systems designed to respond to threats without waiting for human approval. They're not supposed to be weapons. They're labeled defensive platforms, debris management systems, research assets. But if a system can identify a target, calculate an intercept, and deploy a kinetic payload, the distinction between defense and offense becomes academic. The technology has been creeping forward for years. AI-guided satellites that maneuver themselves, avoid collisions, even repair or refuel other satellites without human hands on the controls. Officially, it's about efficiency and safety. Unofficially, it's about getting machines into position before your adversaries understand what you're doing. Because if a crisis hits and you need to act fast, the nation with autonomous systems already in orbit doesn't need authorization delays. The machines are already there. The orders are already written into code. All you need is the decision to activate. The transition has been gradual enough that most people never noticed the line being crossed. First-generation satellites needed constant ground control. Every maneuver required human authorization. Every decision ran through command centers lit up all night. Then came semi-autonomous systems that handled routine operations, flagging only the unusual for human review. Then adaptive systems that responded to predefined scenarios without checking in. And now, satellites that can assess threats, prioritize responses, and execute actions on board, only reporting back after the fact. The human role shifts from operator to observer, and most people don't even realize it happened. Different nations disclose different amounts about what's actually up there. Some publish sanitized manifests, others publish nothing. And the capabilities deployed are almost certainly more advanced than what's publicly acknowledged, because that's how military technology has always worked. By the time the public learns about a capability, the next generation is already in orbit. So, when we talk about autonomy in space, we're probably talking about systems more sophisticated, more independent, and more widespread than anyone outside classified briefings truly knows. Autonomy versus human oversight becomes the central tension. Humans are slow. Humans need sleep, committees, legal reviews. Machines react in milliseconds. They run millions of scenarios and execute decisions before a human has even formed a sentence about the problem. In a military context, that's a massive advantage. In a planetary defense context, it's the difference between intercepting an asteroid and watching your launch window slip away. But it's also the difference between controlled escalation and automated annihilation. The sales pitch is always wrapped in the language of safety. Faster response times, redundancy if ground control is compromised, independent operation during communications blackouts. All of it sounds reasonable until you follow the second-order effects. Because once multiple countries have autonomous satellites in orbit, each running its own threat assessment algorithms, each optimizing for different priorities, you've built a system primed for catastrophic misunderstanding. Connect that to automated planetary defense, and the nightmare writes itself. Multiple nations, multiple autonomous platforms, different protocols, different thresholds, different definitions of acceptable risk. 3 Atlas trajectories start looking ambiguous, and ambiguous is the most dangerous category of all. One country's system decides to launch an interceptor. Another country's system interprets that launch as an attack and responds. Within minutes, you have an autonomous conflict in orbit, triggered by competing AI interpretations of uncertain data. And by the time humans understand what happened, it's too late to stop. The escalation ladder becomes automated. Traditional doctrine includes de-escalation, back-channel communication, the human ability to recognize a mistake and pull back before the spiral. Autonomous systems don't have back channels. They have protocols. Protocols are binary. Either conditions are met, or they aren't. Either the threat crosses a threshold, or it doesn't. There's no room for the kind of judgment calls that have historically prevented catastrophe. The Cuban Missile Crisis ended because humans chose restraint over procedure. Autonomous systems don't choose. They execute. And then there's the training data problem. Every autonomous system is trained on historical patterns, simulated threats, and predicted outcomes. But those datasets don't include interstellar objects performing chaotic gravity assists around Jupiter. They don't include scenarios where legitimate planetary defense activity looks identical to weapons deployment. The AI makes decisions by pattern matching against what it has seen before, and if the present doesn't resemble its training world, the output can become unpredictable. Garbage in, garbage out. Except now the garbage is steering payloads in orbit. Who controls lethal decisions in an automated system? In theory, humans. There's supposed to be a human in the loop, a final authorization step. But if authorization is pre-approved under certain conditions, and the AI determines those conditions are met, does the human truly control anything? Or are they just rubber stamping a decision the machine already made? The line between oversight and ritual approval is disturbingly thin. Pre-authorization becomes the loophole that enables autonomous weapons, while preserving the comforting fiction of human control. Political leaders can claim they haven't delegated life and death decisions to machines because, technically, a human approved the rules of engagement. But if those rules are broad enough, and the AI has discretion in deciding when the conditions are satisfied, then the authorization becomes little more than paperwork and, in practice, meaningless. It's like telling someone they can't fire unless they feel threatened, and then acting shocked when they start interpreting everything as a threat. The framework creates plausible deniability, without creating real control. Now compare the speed of AI to human deliberation. Humans can spend weeks arguing about whether to act. An AI can ingest the same telemetry and execute a decision in seconds. And in some scenarios, speed is survival. Wait for international consensus, and you miss the window. Act unilaterally with human authorization, and you risk being blamed if it goes wrong. But let the AI act autonomously, and you can claim you weren't in control, legally convenient, morally chilling. Accountability becomes impossible to pin down when machines make the choices. There's a temporal mismatch here that no committee can truly resolve. Human decision-making moves in hours, days, weeks. Orbital mechanics move in moments. A satellite in low Earth orbit completes a full revolution in about 90 minutes. A quiet, repeating clock. Threatening objects can cross critical distances in seconds. If you require human authorization for every action, you've already lost because the human can't respond fast enough. But if you remove the human from the loop, you've built autonomous weapons that violate the principles of proportionality and discrimination. Principles we spent centuries trying to carve into the laws of war. The loss of restraint is the real danger. Humans carry friction against violence, empathy, guilt, hesitation, the weight of imagining faces. Machines don't. A human might second-guess an order to deploy a nuclear device. Even in a defensive scenario, a machine won't. It will calculate probabilities, select an outcome, and execute, without a tremor of feeling. And while that might sound efficient, it also removes the one factor that has historically prevented the worst outcomes. People refusing to follow orders because they couldn't live with the consequences. History is full of moments where individual humans prevented catastrophe by disobeying protocol, quietly, at the edge of the abyss. Stanislav Petrov in 1983, who didn't report a false nuclear alert because something felt wrong. Vasily Arkhipov in 1962, who refused to authorize a nuclear torpedo launch during the Cuban Missile Crisis. These men saved the world by being human, by holding doubt, by choosing judgment over procedure. Autonomous systems don't have doubt. They have confidence scores, and a 95% confidence score is more than enough to execute. This ties directly to nuclear interception ethics. If we're going to use nuclear weapons to deflect 3 Atlas, who makes the call? If the decision is automated, delegated to an AI that evaluates threat levels and authorization thresholds, then we've outsourced the most consequential choice in human history to an algorithm. And if that algorithm is wrong, or its training data missed a crucial scenario, or it reads ambiguous signals as confirmation, then we've handed extinction to a machine that doesn't understand what extinction means. The philosophical problem is that machines lack the thing we need most in crisis. Intelligence, yes. Processing power, absolutely. But wisdom is different. Wisdom means understanding context, recognizing uncertainty, appreciating stakes in a way that goes beyond probability distributions. A machine can tell you action A has a 70% chance of success, and action B has 60%, but it can't tell you that the 30% failure case for action A is global nuclear war, while the 40% failure case for action B means we try again. Wisdom is knowing which risks are worth taking and which are never worth taking, and that's a uniquely human capacity we're steadily automating away. Future governance of autonomous systems is, right now, effectively non-existent. There are proposals, frameworks, treaty discussions that would limit or ban autonomous weapons in space, but proposals don't stop development. Treaties don't stop countries that refuse to sign them, and once the technology exists, the incentive to deploy it is overwhelming, because the country that holds back becomes vulnerable. It's an arms race, and arms races don't end well. The governance vacuum exists because the technology evolved faster than the institutions meant to regulate it. By the time international bodies began debating rules for autonomous weapons in orbit, multiple nations already had systems deployed. Any treaty now would require dismantling existing capabilities, asking states to voluntarily surrender strategic advantage. That has never worked. Not with chemical weapons, not with nuclear weapons, not with anything that confers leverage. The window for preventing autonomous weapons in space closed years ago. Now we're managing consequences. The question is whether automation saves us or ends us. Does it provide the speed and decisiveness needed to respond to threats like 3 Atlas? Or does it create new failure modes, catastrophic decisions made faster than humans can correct them? Both answers might be true, and that's the problem. We're building systems that could preserve civilization or erase it, and we won't know which until the moment we use them, when it's already too late to choose a different path. Autonomous weapons in space mirror the asteroid problem. Both are existential risks born from our own advancement. Both demand coordination we struggle to achieve. Both run on timelines that exceed human decision-making capacity. And both may end us not because we intended harm, but because we built systems too fast, too complex, too divorced from human judgment to be controlled when it mattered. The asteroid comes from outside, but the weapons are already here, circling in silence above the weather and the sleep. And if those trigger conditions involve ambiguous threats, tight windows, and high-stakes decisions, then eventually something will go catastrophically wrong. Not because the systems failed, but because they succeeded at doing exactly what we designed them to do: make decisions too fast for humans to stop. Part 14. Part 14. The search for technosignatures goes silent. For decades, SETI has listened, scanning the sky for signals, patterns, anything that would suggest we're not alone. The assumption was simple: intelligence eventually reaches out. Civilizations advanced enough to build transmitters would want to communicate. But the sky has been quiet. Not just empty, but silent in a way that becomes statistically stranger with every passing year. And recently, that silence has started to feel less like a mystery and more like a warning. The listening has been comprehensive. We've scanned millions of stars across multiple wavelengths, year after year. Radio telescopes trained on promising candidates for decades. Optical SETI looking for laser pulses. Surveys searching for megastructures, waste heat signatures, atmospheric biosignatures on exoplanets. Every year the instruments get sharper, the surveys go deeper, the hiding places get fewer, and every year we find the same thing: nothing. The universe, as far as we can tell, is devoid of anyone trying to talk to us. The Fermi paradox crystallizes it into one question: where is everybody? If the universe is as old and as vast as it is, and physics is consistent everywhere, then even if intelligent life is rare, we should see something. Dyson spheres, radio leakage, probes passing through our neighborhood. Any trace at all? The fact that we see nothing despite looking harder and harder starts to feel less like a puzzle and more like a data point. The silence is telling us something, and what it seems to be saying grows harder to ignore. The numbers should favor contact. Hundreds of billions of stars in our galaxy, billions with planets, millions in habitable zones. Even if the odds of life emerging are vanishingly small, the scale should still produce someone, somewhere. But we find nothing, not a whisper. Null results keep piling up survey after survey, each more sensitive than the last, each returning only cosmic static. Drake's equation was supposed to help us estimate the number of communicating civilizations. Multiply factors: star formation rates, planet fractions, habitable worlds, life, intelligence, technology. Early estimates were hopeful: thousands, maybe millions. But as we've learned more, term after term has been revised downward. And there's one term that haunts the whole equation: how long a technological civilization remains detectably broadcasting. Because if that number is small, if civilizations don't last long after developing radio, then the equation gives a colder answer, an answer that looks a lot like the silence we actually hear. The great filter is the hypothesis that makes the silence coherent. Somewhere between life beginning and a galaxy-spanning civilization, there's a barrier, a step so hard, so improbable, that almost no one gets through. Maybe it's the origin of life. Maybe it's the jump to multicellularity. Maybe it's intelligence, or technology, or something we haven't imagined. But the filter exists, and the fact that we don't see anyone else suggests it may be ahead of us, not behind us. That's the uncomfortable implication. We might have already cleared several difficult steps, and still be approaching the one that ends the story. Life on Earth emerged relatively quickly after the planet cooled, which suggests biogenesis might not be the filter. Multicellularity evolved. Complex organisms diversified. Intelligence appeared. Technology followed. We've climbed over many hurdles. So if the filter is ahead, what is it? What stops civilizations after radio, but before they spread across the galaxy? And why would it affect everyone? That implication is worse. Civilizations fail predictably, not randomly, according to patterns that emerge from the nature of intelligence itself. Maybe technological species build weapons before they build wisdom. Maybe they exhaust resources before they learn sustainability. Maybe they create existential risks faster than they create solutions. And if that's true, then the silence isn't a mystery. It's a graveyard. Look at what technologies tend to arrive first. Fossil fuels before renewables. Nuclear weapons before fusion power. Artificial intelligence before we understand consciousness. Gene editing before we understand ecosystems. The pattern is consistent. We gain the capacity for catastrophic harm before we develop the restraint to avoid it. And if that isn't uniquely human but a structural feature of technological development, then every civilization hits the same crisis point, the moment where power outpaces wisdom, and most don't make it through. Connect that to self-destruction narratives, and the pieces fit too neatly. We've had nuclear weapons for 80 years. We've come terrifyingly close to using them, We're building AI without fully understanding it. We're altering the climate without intending to. We're deploying autonomous weapons without oversight. Every new technology expands power without necessarily expanding restraint. And maybe that's the universal pattern. Intelligence reaches a point where its creations exceed its control, and the end tends to rhyme. The list of near misses is longer than most people realize. The Cuban Missile Crisis is the famous one, but there have been dozens of incidents where nuclear war nearly began false alarms, miscommunication, human error. In 1983, a Soviet early warning system mistakenly detected incoming American missiles. Protocol demanded retaliation. The officer on duty decided it must be wrong and didn't report it. He was right. If he'd followed procedure, we wouldn't be here. That kind of human judgment, imperfect, hesitant, deeply consequential, has saved the world more than once. And we're supposed to believe every civilization navigates this minefield successfully, forever. The silence suggests otherwise. Technological maturity versus wisdom may be the gap that can't be crossed. We can build fusion reactors, autonomous satellites, interstellar probes, yet we can't cooperate on basic existential threats. We can split atoms, sequence genomes, land robots on Mars, and still fail to agree on resource sharing, conflict prevention, coordinated response to predictable disasters. The technological curve is exponential. The wisdom curve is logarithmic, at best, and the distance between them keeps widening. Intelligence solves problems. You need more food agriculture. You need to cross oceans, ships. You need to kill more efficiently gunpowder. Every solution creates new problems, and the cycle accelerates. But wisdom is different. Wisdom is restraint, long-term thinking, recognition of unintended consequences. And wisdom doesn't scale the way intelligence does. You can build a smarter AI by adding more compute. You can't build a wiser species by the same method. The silence might be the answer, not to whether intelligence exists, but to what happens to it. They were there. They built. They reached. They touched the edge of interstellar space, and then they hit the filter. The thing they couldn't solve, the coordination problem they couldn't overcome, the threat they couldn't deflect. And the galaxy moved on without them, as it will move on without us. Consider the timescales. A technological civilization might have only a few hundred years between developing radio and either destroying itself or transforming into something unrecognizable. In a galaxy billions of years old, that's a blink. Even if thousands of civilizations rose and fell, the odds of two being detectable at the same moment are tiny. We could be surrounded by ruins and never know it. Because ruins don't broadcast, and bones don't fossilize across interstellar distances. All we'd see is silence. This ties to lifeboat logic on a cosmic scale. If most civilizations fail to coordinate responses to existential threats, then the ones that survive may be the ones that fragment. Small groups escaping to habitats, moons, other worlds, preserving a remnant while the homeworld collapses. And maybe that's why the galaxy is quiet. Survivors are too small, too scattered, too busy surviving to broadcast. Civilization becomes diaspora, and diaspora becomes invisible. Post-collapse remnants wouldn't look like what we're searching for. They wouldn't have planet-scale energy production or sprawling communication networks. They'd be outposts clinging to life, maybe a few thousand individuals, distributed across cold shelters and dim corridors, preserving knowledge and genetics, but lacking the resources for ambition. They might endure for generations, slowly rebuilding or slowly fading. Either way, they wouldn't send signals we'd detect. The galaxy could be full of survivors, and we'd never know because we're looking for thriving empires, not refugees. And if we treat Earth as a case study, we're already showing the warning signs. Fractured coordination, escalating risks, technological power outrunning wisdom, collective action problems we can't solve. If an alien xenoscientist were watching us, they'd recognize the pattern. Late-stage pre-filter civilization, high technology, low cohesion, rising probability of self-termination within the next century. And 3 Atlas, in this frame, is just the latest test. Not the first, not the last, but representative of a whole category of threats intelligent species apparently struggle to handle. From the outside, the pattern would be obvious. A species develops nuclear weapons and keeps building them for 80 years, despite knowing they could end everything. A species discovers climate change and continues burning fossil fuels for decades while evidence accumulates. A species identifies asteroid risk and doesn't build deflection infrastructure until a real threat appears. Always reactive, never proactive, always prioritizing short-term advantage over long-term survival, always assuming coordination will appear when needed despite never demonstrating it. Any observer would predict failure. The only question is which threat arrives first. The final question the silence asks is whether survival is even possible at scale. Maybe small groups can make it. Maybe individuals can adapt. But can a species of billions divided into competing factions with unequal resources and conflicting goals survive its own technological adolescence? The evidence from the galaxy suggests no. The silence suggests the filter gets everyone eventually. And we're approaching it rapidly, eyes open, hands tied, unable to do what survival requires, because doing so would mean becoming something we've never been: unified, cooperative, wise. The answer might be that civilization at scale is inherently unstable. Past a certain level of technological capability and population size, coordination problems become mathematically brutal. Small groups can coordinate tribes, villages, even cities through shared bonds and direct experience. But billions across continents, languages, cultures, histories, interests, that may be asking more than intelligence can deliver, the filter might not be a specific technology or a single threat. It might be the simple, cold fact that cooperation doesn't scale to the problems civilization creates. The search for techno-signatures has gone silent because there's nothing to find. We searched for evidence of survival and found evidence of failure. The galaxy is full of ghosts and we may be next. The telescopes will keep scanning. The surveys will continue. We'll keep listening for signals that don't arrive, searching for civilizations that either never existed or didn't last. And maybe someday we'll detect something, some faint whisper across the stars, proof that survival is possible after all. But every year of silence makes that less likely. Each null result becomes another data point supporting the grim hypothesis. Intelligence may be common, but survival is rare. The universe can produce thinking beings, but thinking beings may not be able to survive themselves. And if that's true, if the silence is the answer, then 3 Atlas isn't just an asteroid. It's an exam. One more test in a long series that civilizations apparently fail, and the galaxy is waiting to see whether we're any different. Part 15, the final question. 3 Atlas is not unique. It's not even unusual. In the last 5 years, we've detected more interstellar objects passing through our system than in all previous human history. Oumuamua in 2017, Borisov in 2019. 3 I-Atlas now, and those are only the ones we caught. For every visitor we detect, there are likely dozens we missed too small, too dark, passing through regions we weren't watching. The rate is increasing. Whether that's because our detection is improving or because there are truly more objects, we don't have a satisfying answer. The detection gap is real. Our surveys cover only a fraction of the sky at any moment. Even within coverage, we catch only what crosses a brightness threshold, something the size of a house, dark as coal, slipping through the outer system. We'd never see it. Something moving through the plane of the ecliptic, while our telescopes stare elsewhere, invisible. The objects we detect are the bright ones, the large ones, the ones that pass near what we already monitor. For every one we spot, there could be 10 more that slid through unnoticed. Statistical models suggest the interstellar population is far larger than our detection rate implies. Some estimates put Oumuamua-sized objects through the inner system at roughly 1 per year. Smaller ones more often, larger ones less often, but not impossible. And all of them are wildcards. We don't know composition, trajectory, or behavior until after detection, which means we're always reacting to arrivals, not preparing for arrivals. Rising detection means rising threat assessment. Every object has a trajectory. Every trajectory has uncertainty. And every uncertainty contains low probability outcomes, where the object meets a planet at exactly the wrong angle and becomes a collision course with something inhabited. We've been lucky so far. Oumuamua sailed through without incident. Borisov did the same. But luck doesn't scale. The more objects we see, the more likely it becomes that one day something threads the needle in the catastrophic way we've been modeling. Probability turns against us over time. Any single interstellar object might have only a tiny chance of hitting Earth. 1 in a million, 1 in 10 million, whatever the number is. But if we're seeing multiple objects per year, and detection keeps improving, the cumulative probability adds up. It's like playing Russian roulette with a million-chamber revolver. Any single pull is safe. Pull it enough times, and eventually the math catches up. And in this case, we don't get to stop playing. Interstellar orbital dynamics make these objects particularly dangerous. They aren't bound to the sun, so their velocities are higher than native asteroids. Higher velocity means more kinetic energy and more destructive potential. And because they arrive from random directions with random inclinations, we can't predict them the way we can with many comets and asteroids that return on known paths. Each one is a fresh surprise, with a unique threat profile, so framing this encounter as a rehearsal changes the emotional weight. 3. Atlas might miss. The probabilities might break in our favor. Jupiter might deflect it safely, or it might leave on a trajectory that carries it far from Earth, and a year from now we might feel relieved and slightly embarrassed about how worried we were. But even if that happens, we've learned something real. Our coordination is fragile, our technology is incomplete, our decision timelines are slow, our incentives push fragmentation over cooperation, and the next time this happens, and there will be a next time, we won't have fixed those problems. This is a dress rehearsal, whether we want it to be or not. Every institutional failure we're seeing with 3i Atlas is a preview of what happens when the threat is certain instead of probabilistic. The coordination problems won't vanish. The political gridlock won't resolve itself by magic. Capital won't suddenly stop flowing toward lifeboats instead of solutions. If anything, pressure intensifies these behaviors. So even if we dodge this one, we're not learning what would help us survive the next. We're confirming that our response mechanisms don't work, and then hoping we won't need them again. The failure modes are becoming visible. We can see how scientific uncertainty gets weaponized to delay action. We can see how international coordination collapses when national interests diverge. We can see how economic incentives steer decisions more than survival instincts. We can see how action timelines are fundamentally incompatible with consensus timelines. All of these are fixable in theory. None of them are being fixed in practice. And the gap between what we could do and what we are doing is where extinction lives. Decision-making limits are species-level constraints. We're not going to suddenly become globally coordinated. We're not going to eliminate sovereignty or dissolve national interests overnight. We're not going to persuade the wealthy to stop prioritizing their own survival. Those structures are load-bearing, adaptive in older contexts, and they won't disappear just because they're maladaptive against asteroids, which means every future threat will slam into the same barriers 3i Atlas is hitting now, and eventually, luck runs out. The structures that helped us thrive for thousands of years are turning into liabilities. Tribalism was adaptive when threats were local and immediate. Competition drove innovation and expansion. Hierarchies enabled coordination beyond kinship networks. All of it made sense in the world that shaped us. But existential threats from space don't care about tribal boundaries or national sovereignty or economic competition. They require coordination at scales we've never achieved, with speed we've never demonstrated, under uncertainty we've never managed well. And we're trying to meet those requirements using decision machinery designed for a different era entirely. Evolution doesn't prepare you for novel threats. It prepares you for the threats your ancestors faced. Our ancestors never faced asteroid impacts requiring global coordination to prevent. They faced predators, rival groups, resource scarcity, disease. The psychological and social machinery we inherited is optimized for those. When we apply that machinery to planetary defense, it misfires. We treat rival nations like enemy tribes. We hoard resources as if scarcity is inevitable, even when cooperation could create abundance. We prioritize immediate, visible danger over abstract future risk. We're running outdated software on modern problems, and it shows. Contrast intelligence with maturity, and the problem sharpens. We are brilliant. We can model complex systems, compute trajectories, design nuclear interceptors, build Mars colonies. But maturity is recognizing that survival depends on people you don't like. That short-term self-interest can lead to long-term extinction, that some problems can't be solved individually, only collectively. And by that measure, we're adolescents, powerful, impulsive, convinced of our own durability, and poor at learning from close calls. Adolescence is the disconnect between capability and judgment. Teenagers can drive cars before they fully understand consequences. They can reproduce before they're ready to raise children. They have adult strength without adult restraint. They're famously bad at risk assessment, especially low probability, high consequence risks. "It won't happen to me" is the anthem of adolescence. As a species, we sing the same song, just with rockets and reactors. We can split atoms, edit genes, alter climate, and we wield that power like teenagers in fast cars, confidence racing, far ahead of wisdom. So, What does survival mean here? Biological continuity? Sure. 800 people on Mars is continuity. Culture can be archived. Databanks, DNA samples, libraries sealed in titanium vaults. But if what makes humanity worth preserving is our capacity for cooperation, creativity, collective achievement, then survival isn't only keeping a subset alive. It's maintaining the civilization that makes those achievements possible. And that's what we're failing to protect. There are different kinds of survival. Bacteria survive. Insects survive. They persist through catastrophes, but they don't build cathedrals, compose symphonies, or explore space. Those achievements require civilization. Civilization requires cooperation at scale, institutions, trust, shared purpose. A remnant population in scattered outposts might preserve human DNA, but not human civilization. Collective achievement depends on enough people, enough resources, enough stability for specialization and long-term projects. Drop below a certain threshold, and you may lose that capacity permanently. What we're risking isn't only lives, it's the entire project of civilization, accumulated knowledge, cultural achievements, the artistic and scientific heritage built across millennia. You can't store that in a database and call it saved. Culture lives in people, in communities, in the living transmission of meaning across generations. Break the chain, and it's gone. No matter how many books you preserved, how many servers you hardened, how many archives you buried, because civilization isn't just information. It's a living process that must be continuously practiced. Priorities, not physics, are the core realization. The physics of deflection is hard, but solvable. We know how to move objects in space. We can calculate trajectories. We can build nuclear devices and fusion reactors and autonomous satellites. Physics isn't the bottleneck. Human priorities are resource allocation, political will, coordination, trust. And unlike physics, which improves with research, our priorities seem to be getting worse, more fractured, more short-term, more zero-sum. We spend more on military budgets in a single year than we've spent on planetary defense in all of human history. We can find trillions for bailouts and subsidies, but planetary defense gets a rounding error. The money exists. The technology exists. What doesn't exist is collective will, the willingness to prioritize long-term species survival over short-term factional advantage. That's not a resource problem, it's a values problem, a choice about what matters. And the irony is, we already know what we'd need to do. The technical solutions are written down, the coordination mechanisms are understood, institutional frameworks have been proposed. We're not failing because we lack knowledge. We're failing because we lack commitment, because the people controlling resources are optimizing for other objectives: quarterly profits, election cycles, national advantage, personal legacy. All rational in isolation, collectively suicidal under an existential sky. Leaving the impact unresolved is deliberate. I'm not going to tell you whether 3i Atlas hits Earth or not, because that isn't the point. The point is what we do in the time between now and finding out. Do we build solutions or build lifeboats? Do we coordinate or fragment? Do we face the threat together or alone? Those are the choices that matter, and those choices reveal who we are more clearly than any impact or non-impact ever could. Character is revealed in crisis, not by what we promise, but by what we do when the stakes are real. Right now, in this moment, we're revealing our character as a species, and what we're showing isn't comforting. We're showing that we'll debate while the clock runs out, that we'll prioritize sovereignty over survival, that we'll choose comfortable narratives over difficult truths, that we'll save ourselves before we save each other. Those aren't accusations. They're observations, patterns of behavior under pressure. And behavior under pressure is the most honest map of what we truly value. Responsibility, not fear, is the takeaway. Fear is easy. Fear is natural. You see an asteroid in the models and you feel your stomach drop. But responsibility is harder. Responsibility means recognizing that survival isn't determined by cosmic luck alone. It's determined by choices being made right now by the people who allocate budgets, write policy, control infrastructure, and decide what counts as urgent. If we fail, it won't be because the physics were impossible. It will be because we chose other priorities. Individual choices aggregate into collective outcomes. Every person who decides their own survival matters more than collective survival adds to fragmentation. Every institution that protects its own interests over coordinated response adds to failure. Every delay, every hedge, every decision to wait for more data, better options, clearer certainty moves us closer to the point where action becomes impossible. And each choice feels reasonable by itself. It's only when you zoom out that the pattern becomes visible. We're choosing extinction incrementally, one rational decision at a time. Extinction is rarely about rocks. It's about choices. The rock is just the test, the filter, the exam that reveals whether a species has matured enough to handle the power it has accumulated. And so far, our scores aren't encouraging. We know what we would need to do to pass. We just don't seem capable of doing it. And maybe that's the real lesson of 3 Atlas and Oumuamua and Borisov and all the visitors still to come. Not that space is dangerous, but that we are, to ourselves. And until we learn how to change that, the rocks are the least of our problems.